Well, welcome back, folks. Looks like we can get started now. Week 7, pretty much our main goals are get through the chain rule, our next big formula for differentiation, and look into the application exponential growth and decay. And this is pretty much almost all of chapter 3. We have one more chapter on the derivatives of logarithms, which is what this review content is all about. It started off way over in section 3.3, but I've been just pushing it down section by section as we go. And we'll do a little bit of logarithm work when we're in section 3.6. So this is good material to start taking a look into, just to brush up on our skills with logarithms. Well, so far, here's what we have for section 3.4, 3.5. The product rule was this differentiation process. We extended to the quotient rule whenever we're dividing by we're dividing a function by another function, neither one of them constant. And now the big new rule is this one, also stated on the notes. The chain rule is really all about what do you do when you have a bona fide function composition, and there's nothing you can do to simplify it, either practically or maybe impossible, depending on the function. The derivative takes on this new format, which is kind of tricky to process at first. But if you can think in terms of what function is on the inside, what function is on the outside, putting this together in the chain rule becomes a process that will feel kind of automatic, kind of like using the power rule after we've gotten a lot of practice in. So that's pretty much our goals for getting through this week. We have our second exam that's coming up. It's going to be on week 9. That's one is, let's see, March 9th. That will be well ahead of spring break. Spring breaks starts on the 23rd. So our exam week will be here on the 9th. And then we'll have a normal week that we'll get through right before spring break. So this Friday, my goal is to just get caught up on grading. Then I'll post the exact coverage we'll be looking into on exam 2, depending on where we end up at the end of week 7. After I post the coverage, my very next thing I'll do is post the formulas that will be included on exam 2 on the very last page. And then I'll start including the review problems, just exactly like we did for exam 1. Well, that's our goals for today and down in the future. Any questions or comments at the moment, folks, before we start? Okay, well, let's take a look at the good old chain rule. We left off here. We looked into what does a chain rule look like in kind of an analogous situation where we're comparing rates of cars to bikes to people on foot. But that whole discussion was really to get us to this point, looking into the chain rule. Let me see if I can target some of that highlighting just a little bit cleaner. The chain rule says you have a function composition, that's f of g, or you could say f composed with g. The definition of f of g is this, f of g at x. And we've seen function compositions come up before, but we've never differentiated them. The major idea is we're thinking of this g of x function as being the inner function. It's a function that goes on the inside. The function f of x, or excuse me, just the function f, composed with g of x, we think of as the outer function. Outer because if there's something that's inner, there's got to be an outer. So that's our organization to when we see a composition. And when you put this together in the derivative, differentiate f of g of x, just labeled as capital F of x in the notes, it has a pretty interesting structure. You go f prime at g of x times g prime of x. And there's a particular order that we always take when we write this down in practice. If we're doing a problem like the ones down below in the notes, we label the inner function as function 2. We label the outer function as function 1, because the order that we typically do the derivative for the chain rule is we differentiate here first the outer function, then we copy something on the inside, then finally we differentiate the inner function second. So differentiate here first, 1, outer. Inside here, we just copy Whatever g of x is, it goes immediately on the inside. Then we multiply, we chain on, that's a thought in the chain rule, a new derivative. That's derivative 2 inner. So where the red dot is, that's the basic recipe for using the chain rule in any situation whatsoever. No matter how weird the function looks, it's always going to be in that process. And we'll make this analogy really concrete. On every chain rule we use, I'll indicate which function's inner, which function is outer. We'll lay down the structure and go in the order that we see it here. Pretty much just like how we did the product rule or the quotient rule. If you can say what the structure looks like, doing the whole process isn't too bad. Well, the purpose of example 2 is we don't know what f or g is. We just know certain evaluations for f and g. But the whole purpose then for example 2 is just to think about how this structure works. After we get through example 2, we'll be applying it to differentiating something like this. It's a ridiculous function, right? It's a degree 3 polynomial on the inside, raised to the power of 103 on the outside. We can't expand this, at least not in a feasible way. This would take pages of work. So we'll differentiate it through the chain rule. But before we get to example 3, let's just hide it there for the moment. Let's get through this one to practice how the formula goes. Any questions about the formula first before we give it a try? Okay, well, here's our setup for functions. The inner function is g of x. The outer function is f, composed with g of x. Our ultimate goal is to compute f prime at 0, but before we even get there, we need to say what is f prime at x. Really, we're just copying the notes, so let's put this down just to kind of get it into our long-term memory, our muscle memory. F prime of x is always going to go like this. You take the derivative of f first. Then you plug something inside. Then you multiply by the derivative of something else. Essentially, every time I write down the chain rule, it's going to be about like this. So that's why we call this derivative 1, the outer function. 1 means we do that derivative first. Then we turn to what the inner function is. G of x in this problem, as in the notes above, you plug g of x in that first slot. You don't differentiate it at all. It's a strict copy it in. There it goes. G of x is in the position. Then you multiply by the derivative of g at x. And this is saying the same thing, but just in different notation with parentheses around saying differentiate what's inside. But I want to show it like this because this is basically what the chain rule looks like. Even if we're doing something that looks kind of nasty, it's the same kind of process. A derivative, a placeholder, then a new placeholder where you differentiate right there. Let me plug g of x back in. So I didn't do much but copy down the formula in slightly different notation. The prime is in a slightly different spot. But now that we have f prime at x, we can evaluate the derivative f at 0 or f prime at 0. So let's go f prime at 0 equals. All we're doing is making a swap for variable x, plug in 0 everywhere it occurred. So this will be f prime at, oh, hang on, wrong color, g at 0 times, and I'll swap the notation, putting the prime on the g function. It's just easier to see it this way. So times g prime at 0 again. I shouldn't say again, just as g prime at 0, and this is copied g at 0. Now we can see the values. And there's quite a lot of values here. This problem is tricky because we're actually not using all of them. We have to know exactly which ones we need to use. But first, here's a g of 0 that we're going to have to evaluate. So we'll use that function value. There's also a g prime of 0, so we'll use this derivative function value. And on the next line, we have derivative f at, first one, g at 0, we're plugging in an 8. So it's going to be an f prime at 8, multiplied by g prime at 0, we don't know the function, so we haven't differentiated it, but we've been told the derivative of that function g at 0 is 4, so we can just plug in a 4. And that handles the derivative at this step here. So now one more to go. We need one more function evaluation for derivative of f, and that is this piece of information. Again, notice how kind of disturbing that is. There's one piece of information that's unused. So watch out for that when you see this kind of problem in the exercises. We're plugging in this value, f prime at a equals -2. So -2 goes here. Multiplied by 4. And so the result of this derivative is we get, oh, forgot the negative sign. Don't forget laws of signs. That's a silly one to drop. We get a -8 as an end result on this one. So that's essentially the essence of the chain rule. Purpose of example 2 is just to see how does the formula go, and what would we do if we have to also evaluate it at a number. Any questions at all, folks, getting through example 2? Okay, the typical, more routine examples, exercises that we would do, is like this one right here, example 3. Let's try it out again. We now know what the functions are. I notice the notation is kind of mixed sometimes. This was an uppercase f of x, defined as a lower f of x of g at x. This time it's a lowercase f of x, so it's kind of mixed up the format here. But that's okay. Whether you call these functions f, g, lowercase f, uppercase g, what have you, it's more about what function is the outer function and what function is the inner function is the most important thing about the chain rule. And when you look at this thing, there's really two overall functions you're dealing with. There's the degree 3 cubic polynomial, and then there's the power function of power 103. But one function is definitely on the inside of the other function, right? The cubic polynomial is on the inside of the power 103 power function. So that makes this whole function right here become the inner. We do that derivative second, so I write 2 inner, just as a bit of bookkeeping, getting started on this process. And it's weird because I'm starting with 2. I'm not starting with the thing I do first, but that's because usually the inner function is the easiest one to spot. It's inside of something else. There's another function, the power 103 function. That's the derivative we handle first, the outer one. The outer function is y equals x to power 103. We certainly know how to differentiate that. 103 comes down as a coefficient in front. The new power is 1 less, 102. But it's not just x on the inside. This is why we're using the chain rule. What's inside is that entire thing. So we're going to put a placeholder where this x is right here when we go to differentiate. So all this is really just setup, bookkeeping or careful analysis before we get started. If we're going to use this formula, we need to know which one is f, which one is g to put it all together. And here's what the chain rule finally looks like. The derivative of f at x for an honest function like you'll see in typical homework exercises, typical exam exercise, we go in order of what we wrote down, outer function first. Differentiate the power 103 function, and we'll get to 103, put a big parenthesis, and raise it to power 102. So that's derivative 1. Again, all I've essentially done is I can't use x because there is no x there raised to a power. So we put in a giant placeholder, really just kind of copying the same strategy we've been using all semester long for our properties. Then we multiply that by something. That's on this level we're putting in the derivative of g at x. So here, what I would write for this portion is another big placeholder. Don't forget the prime symbol as a reminder, you have to differentiate this one. And it's really the same structure we wrote out on the prior problem. Once we have our two placeholders, we take the inner function and we first copy it inside of the f function, the outer one, differentiated. So this is what it looks like in practice. 8x cubed plus 9x squared minus 11x plus 6. We have to resist the urge to differentiate it. It's just a strict literal copy in that information, like we see here in the formula. Then it gets copied here, but there's one extra process. We'll differentiate it next. So put in the same stuff, 8x cubed plus 9x squared minus 11x plus 6. And that's what this original formula is trying to say. You copy the g of x, you copy it again, but then you differentiate it. So there's a prime on that step by the red dot, much like how we have a prime right here. And you know, when you get really good practice on the chain rule, you'll probably often just differentiate and not even write this step. But for the purpose of the notes and actually learning the chain rule, I think it really flows well as a two-step process. So I'll write these out using 2 steps on each one so we can see exactly how that formula goes. Well, that's step 1. We did the derivative of the outer function. When it says 2 inner, that means we're about to take our second derivative right here for the inner function. Any questions before we go to that next step? Okay, let's finalize this. The derivative of f at x is 103. That's a horrible 3. Let me start over. 103, 8x cubed plus 9x squared minus 11x plus 6 raised to power 102. And we're going to multiply it by the derivative of this. Notice it's all copying until this stage. But now we just do term by term differentiation. The constant multiple rule and the power rule combined here to give 3 times 8 for a coefficient 24. Power in x is 1 less, so now squared. Then rinse and repeat, plus 18. X to power 1, so just an x. This one has power 1. Sometimes it's kind of fun to visualize it that way, but that's optional. 1 multiplies a negative 11, give you negative 11 x power 0, but we leave that just as negative 11. Really, it's a negative 11 times 1. Derivative of the constant 6 goes to 0, so we cap this off, and that's the entire derivative. But we did it, folks. This is differentiate a function using the chain rule. Is a chain rule absolutely required on this one? No, but for all practical purposes, nobody wants to expand a polynomial of 4 terms to power 103. That's a lot of terms. So this is really the only feasible way to do it in the amount of time we have for class. Well, any questions or comments, folks, getting through that very first one? Okay, what we need to do next is just practice. Then we'll look into some applications. We're going to do another tangent line kind of problem, and then we'll look into a blood flow application to end the notes. So here's the next very typical chain rule kind of problem, part B. We'll be copying this down on the notes just to analyze how these go on each and every one of these problems. And part B, it's not too different from this one, except we want to do a little bit of algebra to clean it up first before we start. Yeah, so this right here, right where the red dot is, would be the answer on this problem. Thanks for asking about that, Mary. This one ends right at this step because with the power 102 here, we really can't expand it. It's already in a nice factored form, so we would always just end right at that stage. Other questions so far? Awesome, thanks for asking about that. And you know, that's going to be kind of another question that comes up on this one. This one's a little bit more messy algebraically, so it's always a good question where to stop on these kind of things. And so I'll try to indicate that as well on this one. So trouble with this thing is when you look at this derivative, it's not really the quotient rule at all. A constant in the numerator means we can completely skip the quotient rule, which is a great idea because if we try to combine the quotient rule with an honest chain rule problem, it gets really messy fast. So the very first thing we're going to do on this one is re-express what the fifth root is in the first place. It's a fractional exponent, power 1/5. So the original function f of x is really 2x squared minus x to power 1/5. I want to put a little border here just to say we're done with the problem above, but we still want to view it just to compare what we did on the last one. Now we can completely skip the quotient rule once again, and we should if there's a constant in either numerator or denominator, by just changing the sign of that exponent. It bumps it up into the numerator. And so now our function is 9 times 2x squared minus x to power negative 1/5. It's essentially the same problem as the last one, except the exponent is not 103, it's negative 1/5. That's a much more complicated exponent in its own sense. There's also a coefficient in front, but the constant multiple rule says when we differentiate, we just pass through this constant because it's multiplying, and we do all the differentiation here. 9 is just going to multiply the result of this derivative. But we can analyze it in the same way. This is a function composition. There's an inner function, 2x squared minus x. So we'll call that function 2 inner. There's an outer function, power negative 1/5. So we have another power function, just like in the last exercise. So this is function 1, outer. And I'll write the outer function specifically as y equals x to a power negative 1/5. You don't necessarily have to say that, but if it helps to visualize, not a bad step. Finally, we're going to differentiate exactly the same order we did this one. But in this format, we can say f prime at x is now equal to, constant multiple rule says, just copy that 9 down. And now we're done with it. It's kind of nice. Then we do the outer function first. For differentiating something to the power negative 1/5, you would get a negative 1/5 coming down. Then the new exponent is going to be 1 less. So we take negative 1/5 minus 5/5 to get negative 6/5 as our new exponent. And we're not done because what was on the inside wasn't just x. If there's a 2x, if there's an x plus 4, anything beyond an ordinary x says now it's a chain rule process. So we multiply it by another derivative that goes here. So far, even though the function looks radically different than the one in part A, we can make it look very similar by doing a bit of algebra, exponent surgery on it. And now the process is the same. We are on this level. We did derivative 1 outer. We blew a hole with parentheses for one input, another one with an input which will differentiate. The function that goes inside both of those placeholders is 2x squared minus x. So far, exactly what we did on the part A problem. And that means we're just about done. All we have left to do is this one derivative. But let's take a look at this carefully. Any questions to this stage? Okay, last thing to do is simplify this a little bit. We definitely need to simplify constants multiplying. So we can rewrite that portion as f prime of x equals negative 9/5, reduce the fraction if it happened to reduce. And here's where we make a judgment call. I'm always totally happy with the negative exponent. So you can leave it just in this format if you prefer. 2x squared minus x. Power negative 6/5 is totally fine for me. Then we move on to this line. Here we're doing more than just copying, we're also differentiating. But we've differentiated these before. This would give us just a 4x on the first term. Derivative of a negative x just gives us the coefficient, negative 1. Then again, at this stage, we're done. If you decide to put this whole term in the denominator, this whole factor really in the denominator to force the exponent positive, that's not a bad step to take. But it's always going to be a judgment call. Let's write that in just to show what it would look like. So if we fix this exponent, force it to be positive, I would keep the -9 in the numerator. It would multiply the group 4x minus 1. Then 5 is going to stay in the denominator. It would multiply the group 2x squared minus x to the power, now a positive 6/5. And just to emphasize on the notes, both are full credit answers. They're fully acceptable on any quiz or exam situation, whether you stopped here or you went that extra step to that next line. In fact, if you did this as an exam question and you just made a mistake here, I'll mark the mistake and then I'll just accept this line as full credit. Well, any last questions at all, folks? Getting through those two chain rule processes? Okay, we still want to practice more because, the hardest thing about chain rule is identifying what function's the inner, what function's the outer. It's not always super straightforward. So what we need is just a lot of additional practice. And for the problems I have below, these ones get a little bit more challenging. So let's maybe do one more warm-up problem before we do the next two below in the notes. So I'll call this one, it's a problem we're inventing out of the thin air. So let's call it a warm-up problem. Same instructions, we want to differentiate or find the derivative. And this time it's going to be a function f of x equals the base e exponential. So this makes it come back e to the power of, let's go 2x squared minus 3. This one's kind of a tricky one because a lot of the problems that we deal with the chain rule sometimes feel quite a bit different if you change to, say, an exponential function or a logarithmic function, say in section 3.7, which are coming up later. First, let's review the things that we know about this problem. If y equals e to the x, we can say immediately that y prime is just e to the x. Kind of a nice formula altogether. But that's not the story this time because the input function is 2x squared minus 3. The input is not just a variable x. It's an entire function of x. So let's write out what the organization should be for the chain rule this time. The function that we consider to be inner is that, the 2x squared minus 3, the function that's replaced the x, or I should be pointing here, replaces the x on the e to the x function. So this time, that function is derivative 2 will take inner. And what do we have left? We have an exponential function. It's really e to the x, but if we were to highlight something or point at something, it would just be the base we point at. This is telling us that function 1, outer, is a function of the form y equals e to the x. We just happen to have done a function composition. We threw something else inside there, 2x squared minus 3. So this is the organization to start in terms of inner function against the outer function. Now the process says when we differentiate, we first differentiate that outer function, the base e exponential. Before we get started, any questions at all, folks, on the bookkeeping organizational step? It definitely does look like E is the inner. And I think the reason for that is when you look into, say, this problem right here, it kind of flows the way this one would. The thing that was on the bottom we considered the inner, and the thing that was on the top we considered the outer. So thanks for asking about that, Naomi. That's what makes this one really, really tricky. But here's a really great process for kind of determining once and for all, which one is it? Is it inner or outer based off whatever your function looks like? What you want to do is throw up a quick calculator. Now we have two functions here. We have a f of x function, uppercase, and a trickier lowercase function, f of x. But let's suppose we want to, in this format, calculate a value of that function, f of x. Let's say x is 1. The question is, what exactly would you do if you're trying to evaluate this function at x is 1? You wouldn't do anything with this part whatsoever, right? You would have to first start here, plug in a 1. You would take a 2 times 1 to power 2, and then go minus 1. This is now just really following order of operations. The next thing you would have to do by order of operations is raise it to power negative 1/5. So we put parenthesis around it, go power negative 1/5 altogether. Then we'd have to multiply it by 9. So go up to the front and take 9 times that result. So what happens here this time? If you were to evaluate this function at, say, same value, x is 1, well, order of operations tells you the very first thing you have to do is plug the input variable value of 1 inside the innermost function, whatever it happens to be. Here, the inner function was the 2x squared minus x, but this time in the function composition, the inner function is 2x minus 3. So by order of operations, we have to do that entire thing. The exponent is the group. 2 times 1 to power 2 minus 3. We do that first, and then we raise it. We take the basic exponential, and we make that the exponent. We would go next, associate, make this become e to a power. Oh, that's tricky. E to a power, I'll use the step there, and you would get that as a result. So that's one way to think about it. In terms of what you would do to do an evaluation, the very first computation through order of operations tells you which function must be inner. In this problem, the first thing you do is square your input, multiply by 2, subtract 3. So it's the inner function. On this one, we square the input, multiply by 2, and then minus the input. So that was the inner one there. That's one way to think about it. And again, that's an excellent question. That's the major reason for this warm-up, supposed to be an M there, problem, is to really tell the difference between this class of functions versus the exponential ones. Does that help out so far, telling the difference between inner and outer? Awesome. And I find that explanation, thinking in terms of order operations, helps some people, but not everyone. Some people think differently about this problem. So if you're the other kind of person that thinks more just strictly about function composition in determining what is inner and outer, here's the second explanation. When you look at this arrangement, e to the power 2x squared minus 3, there's really two functions there for sure, right? There's an f of x function, there's a g of x function. We want to do f equals f composed of g at x, because that's what the chain rule is all about, right? If we can extract what is f and what is g to reform the composition and get the original function f of x, that's this one, we will absolutely know what is inner and what is outer. So thinking in these terms, my claim is f of x, the one that we think is the outer function, sorry, pointing here, is really e to the x. And that the g of x, the one that we think of as inner, is really 2x squared minus 3. But we have to prove that. We prove it through actually doing the composition. So this becomes a good pre-calculus type algebra review. We're going to do this composition here. Here's what it would look like. We would say f, I should really say f at x. Let me fix that right there. That was kind of lazy notation. F at x would become equal to f at, well, I claimed my g of x is 2x squared minus 3, so it just goes right inside there. 2x squared minus 3. So that's the first part of the composition. You unpack what g is. In the second step in the composition, you unpack what the f function was. F was supposed to be e to a power. I'm going to write it like this with a placeholder. You could drop the placeholder if you like. But the thing that's going inside this e to a power function is that 2x squared minus 3. So it goes down, really up, because it's an exponent. It goes up inside that position there. So that's another way to think about it in terms of what is outer, what is inner. But in all honesty, they're very tricky problems. So that's why this warm-up problem was really, I'd say, a necessary one. I probably should have put it in the notes when I first wrote these notes, as this being, say, part C, rather than the one below. And the thing that's tough about it is, again, pattern recognition sometimes completely breaks. We have to watch out for certain functions, and this is the first big pattern break, the exponential functions. Well, any questions at the moment, folks? Getting through really the hard part, analyzing what's inner, what's outer. Okay, the next step is follow the recipe down below. It's essentially a cookbook for handling any function composition, no matter how weird, and they can look very weird like this one, no matter how weird they get, it's always going to be this. So we can say, following the process very, very carefully and very literally, f prime at x is going to be first the derivative of the outer function. But the outer function is e to the x, and its derivative is itself. So it just looks funny when we do this. What I would write down on paper is, here it is, the derivative of e at any input goes like this. The only change I made was I put a parenthesis around that x because we have more going on than just x. We have an entire quadratic. Then on the next step, we chain on a derivative like that. So we have the outer function's derivative is done. Derivative of e to the x is e to the x. We just put a huge placeholder for what the x is. We multiply by some other derivative. And next step, we copy in the g of x function. G of x is going inside the derivative of f of x. That means it's going right here. Back on paper, it's going in this spot. 2x squared minus 3. Then we multiply by the derivative of that 2x squared minus 3. And once we get to here, we're just about done. We just have to finalize that last derivative, and then we are on our way with this problem. Any questions to this stage so far? Okay, let's finalize this. The derivative of f at x is e to the power. Typically, we would drop parentheses, but if it's helpful for visualization, there's no harm leaving them there. E to the power 2x squared minus 3. Just make sure you write it as a superscript, so it has to be above to convey it's all an exponent. We're multiplying by this derivative. That'll be just times here, 2 multiplies the 2 for a 4, x power 1, or just a 4x. The constant goes to 0 because it's not multiplying. We're subtracting a constant. And that's the whole result. It might look a little bit funny like this because usually we would put 4x in front of the e to a power of something. But just to convey that this is totally fine as is, let's leave it like that on this one. So definitely the tricky derivative of the day. But you know what? We've seen something like this back in the notes. Let me open up the 3.3 notes because we've actually done something very, very similar. Uh-oh, somewhere in these notes, I can get the windows to not get angry. Let's scroll through here while we're looking at that last one. Yeah, here's where we first did the derivative of e to the x through this formula that was provided. And let's see. Okay, somewhere, I'm pretty sure we had a tricky derivative. Looks like I did put in the solutions on this one. I'm gonna have to fix that in the notes. It was that one. This derivative was very tricky, so we made a pretty big deal out of that. Let's revisit that just to see how this goes. I need to make a note that for some reason it looks like I didn't upload all the solutions to 3.3. Sorry about that. Yeah, thanks for mentioning that, Haley. Yeah, this one, we made a really big deal out of it when we solved this, but let me also put in a quick reminder. Upload the 3.3 completed notes. And if you ever, by the way, notice some notes are missing, don't hesitate to ask. I'll be very happy to upload them. So this was e to the power w plus 1 plus w. Let's do this one as well in view of what we've been doing so far with the chain rule. So another warm-up problem, but the chain rule is tricky, so extra practice is never a bad idea. So here's our next one. I think I have this solved. Let me double check on the notes. I would just want to compare with what we did if possible. Get rid of that. So we made a big deal out of this one, and we kind of did the derivative in a very roundabout way when we finally went through it. I think there was a lot of discussion on this one in class now that I'm seeing the notes. When we went to differentiate this, we made a big deal out of the fact that w plus 1 does not actually fit this formula. If you put something other than an x or a w in this case for the variable, you have to be very careful on how to work this out. So we went in a really crazy roundabout way of breaking down the exponent so we could get an e to the w. We got a constant, and that was its own set of trickiness because then we're using the constant multiple rule with a very tricky constant. So this is what we did back in the day. Let's do it again and see if we get that as a result. So let's come back to that slide in a minute. But work out this fresh problem. There's actually two rules we have to use. Chain rule right here, and then the sum rule, and I guess three rules, that's the power rule, that will turn into just a one altogether. The main difficulty is right here. We'll organize just like we did on the last one. The inner function is the variable w plus 1 that's being plugged in on the inside of the exponential. So that's the function 2, inner. The outer function is the base e exponential. We have to handle that one first when we navigate through the chain rule. So now we're ready to differentiate on this very first term. I still want to write it down in this organization just so that we can really internalize how this all comes together. So we'll say differentiating this term, z prime, is going to be first the derivative of the outer function. The derivative of a base e exponential goes like this, e to some power. But because it's a chain rule, we multiply it by the derivative of the inner function, so we place a derivative there. The function that's inner is w plus 1. So it goes into those two spots. And then finally, the not so bad part is the derivative of w, think of that as an x, derivative of w with respect to w is just a 1. But here's what we get with the chain rule so far. And, oops, sorry, wrong slide. There it is. We got to e to the power w plus 1 plus 1. That was only because it just so happened by sheer luck, the derivative of w plus 1 is 1. So it was just 1 times e to the power w plus 1, matching up with what we did here. It could have gone totally differently. If that's 2w plus 1, the derivative of 2w plus 1 would have been a 2, and then our answers wouldn't have matched up the way we expected. So this one was just a fluke. If the derivative comes out as 1, and you just forgot to use the chain rule, you match up with the answers. We didn't forget it was a big problem. We just navigated it in a different way. But here's how the end conclusion goes on this one. We get z prime equals e to the power w plus 1. I want to put in a times 1 just to say we didn't forget the derivative. It's right there. Plus 1. But then it just ends at e to the power w plus 1 plus 1. So again, this one was really tricky in the notes. There was a lot of excellent questions about what exactly is going on when we went through that. But now we have the chain rule, this derivative is faster. And the chain rule was more of a formality. It wasn't necessary here, but a really good practice because, again, if it's a 5w plus 1, a 5 would have popped out right in that step, and we could lose the question if we didn't spot it. Well, we took some extra time on these notes just to consider the exponential functions. Again, that's a really good idea because we'll look into 2 more tricky chain rule problems, but we're going to look into even more exponential functions. So to see how it goes on these ones, it's good to know how it went on the base e exponential. This is the first time we've seen this formula, so we'll come back to this one. Well, first week, I've been mentioning there's a couple more challenging problems. In the homework exercise, there's a couple that look about like this. So we'll be careful as we practice these ones next. First, because we're still learning the process, let's place the chain rule down below. What makes this one challenging is the reminder with both part C and part D is that every new differentiation formula that we pick up can interact with every other one that we've seen so far. And when you look at this, there's a function where it's a composition with a power 4 on the outside, multiplying another function where it's a cubic raised to a power 8 on the outside. This one starts with the product rule, then it goes into the chain rule next. So we're using 2 formulas at once on this one. Product rule. Then, after we analyze the product rule, we'll do the chain rule. The hardest part about this is actually not those 2 rules working together. The hardest thing about this one is the algebra. So we'll take our time working out the algebra as well, but it's good review of algebra at the same time. Well, for thinking product rule, here's how it goes together. The derivative of g at v is 2 functions multiplied. So the power 4 with a composition on the inside multiplied by the power 8 function with a composition on the inside as well. We're going to take the derivative of that first function, and it'll look like this. 2v squared minus 7 power 4 prime. So we've differentiated the first. We copy in the second and multiply. V cubed plus 5v minus 1 to power 8. Then there's a plus in product rule. But this time we're copying the first one, 2v squared minus 7 to power 4. We multiply it by this function, but we also differentiate it. And I think brackets are going to look just a little bit easier visually. Let me convert this to brackets. Too many parentheses has a way to kind of get us sort of lost in the weeds with these things. So derivative here, copy, then copy, and a new derivative here. So with a bracket to emphasize, v cubed plus 5v minus 1 to power 8 prime. So that's our product rule in its full glory. I didn't color code this one because the major thing we want to focus on is the chain rule in the next line. Well, any questions at all, folks? Just writing down the product rule to start. Hope that didn't work. Sorry, I thought that might look kind of clean if I brought that back. But here's our product rule altogether. Now notice there's 2 derivatives remaining on the table for us. One here, like a typical product rule. But both of them are chain rules. There's a chain rule here and a chain rule here. It's not the tricky one with the exponential, but there's a good amount of work to do. We have an inner function on this one and on this one here. So let's organize just like before. It takes some time, but it's well worth the effort. Sometimes with these bigger problems, if you go slower, you're really going faster. So let's go slow and careful. Function 2 inner is the quadratic on this one. Function 2, derivative 2 we take, inner, is a cubic function we see here on that second term. Then we have power 4 and power 8. Those are the outer functions. Function 1, outer, is the power 4 function. And I'll just briefly say outer rather than the y equals x power 4, since I ran out of space. Here's the outer function on this one. I have a little bit of space, so I'll just specify that's the outer function in the form y equals x to power 8. So in our next line, we'll navigate to two chain rules, but they're not the worst ones we've seen. It's just a lot of stuff, a lot of writing on each line by line basis. Okay, any questions to this stage of the analysis? Okay, let's work out the next step. Derivative of g at v is going to be equal to, let's get started with this derivative here. Still following the flow that we saw below, I'll punch open two parentheses, one with a prime on it, one copy, but we go in order. Differentiate the outer function first means you get 4 times something raised to power 3. Then you multiply, chain on a new derivative. After all that's in place, you copy in 2v squared minus 7. You copy it here, but also differentiate. Either at this step, if you feel fluent in the chain rule, you might have just put a 4v here. But to break it down stages like before, I'll copy it in and differentiate on the next line. 2v squared minus 7. So that was this derivative. We copy all the way up to that bracket, so times v cubed plus 5v minus 1 to power 8 plus 2v squared minus 7 to power 4. And then we do the chain rule all over again. But it's really the same kind of structure. It's just a different power, a different polynomial. It's a cubic this time. So follow the process. If you differentiate a power 8 function, 8 becomes a coefficient. The new exponent is 1 less, is 7. Now the chain rule takes over. We chain on a new derivative. With those two parentheses, they're meant to fill in here and here with g of x. The inner function, v cubed plus 5v minus 1, v cubed plus 5v minus 1. So we started with the product rule. It ended right on this line. It's done. But we had to now complete all derivatives. So we went to the chain rule. That gave us an extra derivative here and an extra derivative here, since we navigated two chain rules at once. Once we complete those derivatives, we have the answer, not in simplified form, but we are done with the calculus on the next step. Well, any questions at all, folks, to this line? Okay, there's not a lot of problems like these. I think there's a couple in this homework section. And I'm probably not going to ask too much problems along these lines on a real exam. We're doing it here on the notes just for the sake of practice, using more than one rule at once to help out with the homework. And if we can get through a problem like these, the typical exam questions are usually a little bit more shorter, much more manageable. We'll be in really great shape for maneuvering through those. So think of part C and part D down below as just the challenge problems before we go to more routine exercises. So next thing, g prime at v. I'm going to copy all the way to this step where we take the derivative. So we'll have 4 times 2v squared minus 7 to power 3 times this derivative just becomes 4v. The constant goes to 0. I'll place that in green just to emphasize we differentiate here. Then we're copying all the way up to that line. So it's going to be times v cubed plus 5v minus 1 power 8 plus 2v squared minus 7 power 4 times 8 times v cubed plus 5v minus 1 to power 7. And my hand is legitimately getting tired at this point. But here we are all the way to this end. Take this derivative. It's a cubic polynomial, so we're going to get 3v squared, now quadratic, plus 5. We need parentheses on that one because it comes in as two terms. And at this stage, the tragedy with this problem is it simplifies. It actually simplifies a lot, but it's a good amount of algebra. Right at this step, the calculus ends. So if this was an exam question, I think it's kind of a nasty one, but if it was, I would probably give full credit right at that red dot because I want to emphasize the calculus over taking a whole bunch of algebraic steps to simplify. But you know what? In chapter 4, sometimes we do have to simplify things, not quite this ugly, but we do have to simplify things by factoring. So think of this as a warm-up process to something we really legitimately have to do in the next chapter. The first thing I'd want to do to simplify this is maybe bring the 4v and the 4 together, the coefficient 8 out in front, really just organizing. Then we're going to factor out to the greatest common factor. Haley says, I think I like calculus more than algebra now. Yeah, I agree with that. Sometimes the big hurdle is the algebra when it comes to calculus. We're absolutely seeing that here. So think of this as like just some weird puzzle, something extra that's going on top of the calculus. It has its uses because we will factor and simplify derivatives later on. But again, this one is a pretty big one. So as far as that puzzle goes, the more you can organize it, the easier it is to look at. And if you're looking at that 4, so am I. Sorry, that should have been a V. Must have been having two thoughts at once. So there's the V. That's a less of a distraction. Now G prime at V, I want to bring in 4 and 4V together for a 16V. Let's hide the chain rule because we are done with it for the moment, focusing on algebra. 2V squared minus 7 power 3 v cubed plus 5v minus 1 to power 8. Over here, I'm going to bring in 8 as our coefficient, then 2v squared minus 7 power 4 v cubed plus 5v minus 1 power 7, 3v squared plus 5. Okay, so I didn't do much, just kind of made it look a little bit nicer. Now we have a greatest common factor. We can factor out power 3 on this term because it appears in both terms. We factor out the smallest power. We can also factor out between the 16 and the 8. We can factor out an 8 as well. So let's do these in stages. G prime at V, factor out the 8 first. Then I'll put some temporary highlighting. The next level of the greatest common factor involves base 2v squared minus 7. The greatest common factor will only allow us to take the smallest power that we see there, so power 3. 2v squared minus 7, power 3 will then factor out. Then the next common factors we have involve base v cubed plus 5v minus 1. Shows up in two spots. We can factor out power 7. That's the smallest exponent that occurs. So go v cubed plus 5v minus 1 to power 7. Now when we factor all that stuff, think in terms of factoring out a greatest common factor is a type of division problem. This 8 divides the 16, leaving a 2v. So 2v comes from over here. Because we're factoring out the power 3, this entire 2v squared minus 7 power 3 is gone. It completely cancels. We're factoring out a power 7. That means the exponent 8 drops to an exponent of 1. We have behind just v cubed plus 5v minus 1 to power 1, so we don't write in that exponent. We go across addition and do it all over again. But also think in these terms, if you're verifying your work, you'd multiply here to here. You'd use the distributive law. You take 8 times 2v for a 16v. 2v squared minus 7 would go here to power 3. And v cubed plus 5v minus 1 to power 7 will multiply here. The power would bump up to power 8 because there's already another factor. So let's go carefully on the next line. We're factoring 8, so it divides here. That coefficient is gone. If we factor out to power 3 on this base, 2v squared minus 7, this becomes a power 1, 2v squared minus 7. And we factor out this entire term, factor right here. It nullifies this one because the exponents are the same. All that's left over is the 3v squared plus 5. Okay, so we've factored it a little bit, but now we've opened a new can of worms because if we distribute in 2v here and FOIL here, we can collect like terms. But the end is near. There's just 2 more steps, and this was the tricky one, getting out that greatest common factor. That right there where the red dot is an important skill in chapter 4. So it's kind of a preview, although this problem is a little bit more messier than what we'll see. Well, let's go to the next line. G prime at v is 8. I'm going to copy all the way to here. 8, 2v squared minus 7 cubed. V cubed plus 5v minus 1 to power 7. Now hit it with the distributive law. We get 2v power 4 plus 10v squared minus 2v. Over here, ordinary distributive law plus 6v power 4 plus 10v squared minus 21v squared minus 35. We have several sets of like terms, so that's our last challenge to navigate. Any questions so far to this stage? Okay, we're almost there. This is kind of not the worst problem in the world for the calculus, but a very messy algebra problem, but we nearly are at its completion. G prime at v becomes 8 2v squared minus 7 v cubed plus 5v minus 1 to a power of 7. My penmanship is kind of going down. Let me revise that. I'll leave it a bracket just to show where the next result is coming from. And now it's a 2v squared, 2v power 4 with a 6v power 4, so 8v power 4 altogether. The next term is 10v squared plus 10v squared up to 20 of them minus 21v squared balances out at negative 1v squared, or just negative v squared for short. Next one is power 1. We have a negative 2v, and that's it. So negative 2v. Next one is v power 0, or rather just the constant term, really. And the only constant term we have is clear over here, negative 35. That's a good moment to celebrate because that's the last bit of the algebra. Again, this one is nasty. I don't think the homework gets quite this bad, but a couple of them do get messy. If you're working any problem in the homework and you're noticing the algebra gets messy, don't hesitate to reach out. I'll be happy to help, or maybe even suggest it as the first problem of the day to start us out. But once again, all of calculus ended on that step. And we have an interesting view on this. This is a complicated function. The derivative of this function is even more complicated. But at any value v I plug in, it will tell us exactly the slope, the tangent line to this original equation. So it's always a good idea to reflect on what is the derivative even giving us. It's giving us a slope, no matter how weird and wild it gets. And we'll return to a tangent line problem just to emphasize that before the application problem in these notes. Well, it looks like we have about 9 minutes and some change. Our next problem is along a similar lines. Sorry, question first. Oh, good eye. Yeah, right here is a power 3. Thanks for spotting that. And you know, that's the tragedy with these kind of problems, working them out. Say as a WebAssign problem, forget one little thing and then it rejects your answer. So let me highlight that. Right here, should be a power 3. That's one of the worst mistakes to make, a copy error. But when there's so much stuff, there's actually a high probability of making at least one copy error like that. Other questions or comments so far? Okay, we're going to deal with another challenge problem, this one down below. I feel like this was going to be a good one to come back to on Thursday. That way we're not going to rush through this one. Really the theme on this one is it's a mixture of first a chain rule, then a quotient rule with what we have on the inside. It's actually not as bad as the last one. It just sounds bad, but it does get kind of messy algebraically. So we'll take our time with this one. After we complete that, we'll be looking into this new theorem. At this point in the notes, once the author develops the chain rule, there's some optional topics that in the reading, you're free to skip. The longer chains, which means your function composition with more than 2 functions. Implicit differentiation is a whole brand new technique, as is related rates. We're, in brief calculus, not going to cover all those concepts. That would make it a 4-credit class. But our author uses this idea right here. This is optional reading. It can be skipped. But the idea of implicit differentiation gives you this formula. We have a little bit of time to look into this one briefly. So let's take a look into this. It's saying the derivative with respect to x of b to the power of x is b to the power of x again times the natural logarithm of b. And that's a pretty weird formula. But you know what? We have been using it all along. Recall we have a formula that goes if y equals e to the x, its derivative, y prime or dy dx, is e to the x. But actually, it's this formula all along. We just happen to hide the fact that we were using that and simplify it. So if I backtrack and say if y equals e to the x, it really works out this way. Then y prime equals e to the x. That's the first step where the red dot is. We multiply by the natural logarithm of e, and this is where properties of logarithms come into play. It just so happens to turn out that the logarithm to the same base is always a 1. So for example, in the calculator, just to emphasize, if we say take the natural logarithm of e, the natural logarithm is just log to base e. So log base e, that's what this is saying, at e itself, that's just a 1. So we use this formula directly. We just happen to simplify it. That's a 1 right there. So this becomes y prime equals e to the x times 1 equals e to the x itself. The formula becomes more interesting if you're dealing with something that's not to the base e. So for a different exercise, if y equals 2 to the power of x, now we really have to use this formula. The derivative of this function through the formula is going to be y prime equals 2 to the power of x times the natural logarithm of 2. So we get that as a result, differentiating this function right here. And example 3 is asking us to do 3 different derivatives. But really, this is a big comparison type exercise. We have lots of differentiation formulas on the table now, and sometimes it's easy to mix them up. This one uses the power rule, but this one's an exponential function, and this one's an exponential function together with the power rule, excuse me, the chain rule. Sorry, kind of had a brain sleep right there. So let's do a couple of these, and we're going to save this one for last as well. So if we're differentiating y equals x cubed, we know how to do that. We'll use this idea. Power rule because it's a power function. Why is it a power function? It's because x is the base, not the exponent. So if we have y equals x cubed, this one's not too bad. You would say y prime is 3x squared. But now it's confusing when you change it up. If you flip, what's the base and what's the exponent? It's not the power rule at all. This one is an exponential function. So if you have y equals 3 to a power of x, the derivative on this one, y prime, is itself 3 to the power of x, much like with the base exponential. But then you get a little bit more tacked on. You have to always multiply by the natural log of 3, or else we actually don't have the full-on correct derivative. It's just a fluke that that number e is extra special, Euler's constant, approximately 2.71, where this is the one and only function where you differentiate it and you get itself. Any other function or exponential function has something more when you go to differentiate. So this is a very mysterious function. The more differentiation formulas we start to pick up. This one will be tougher because we have to use a property here for exponential functions and the chain rule. So that'd be a good one to come back to. So for the moment, we're ending class on just the major thing to watch out for. Watch out for a power function like this versus an exponential function, because the results for what you get on the derivative are completely radically different. Well, any last questions at all, folks, with where we ended on here today? Okay, this is kind of a weird spot to end on because I have almost 4 minutes, but the next questions are just longer. We're going to differentiate a square root function, do a tangent line problem. Then we'll do an application problem with the chain rule. And this is a pretty interesting and relatable problem. This is about, let's see here, the dilation of a blood vessel, whether it's in your arm, in your heart, in your brain. The dilation of a blood vessel is an important medical thing. Some people who might have, say, angina take a medication called nitroglycerin that opens up those blood vessels to allow the blood to flow naturally to remove that pain. And we're going to look into the speed of the blood itself as the artery becomes bigger, dilates. It's really a chain rule problem out of nowhere and an important medical biological problem. But we'll be sure to make sure we do all the problems that we left behind. A tough chain rule problem, a tough chain rule problem with an exponential, and a tangent line problem. Have a great night, folks. If you have any other questions, I'll be happy to help out, but we'll return right here next time in the notes. Have a good one, folks. Yep, take care.